Oh, hi there. Thanks for showing up for your learning. Once again, you continue to do this, and I continue to be appreciative of this time that we get to share, where I get to discuss cool math concepts, and we get to wonder why it's not showing up on the projector. Well, that's strange. Let's see, maybe the problem is in here. Oh, this is going to be a great video, really useful for the people at home. No, that's not the problem. And then I did this up here, source search, and then it will find my computer right there. Yeah, I'll watch Mr. Jennings struggle with his technology and eventually succeed. Ah, the powers of the growth mindset. If it doesn't work, try everything, and then eventually it will work. All right, so if I gave you problems like this, 4 to the 1 half multiplied by 4 to the 1 half.
Yeah. Isn't that just 2 or 3 times 2? Because you just multiplied 4 by 0.5?
Oh, well, how about this one? 27 to the 1/3.
So that's
Maybe we should talk about that one then.
9 times 9 times 9.
Yeah, but it's not going to be that, and I'll show you why. Okay, and this one is going to be 2 times 2, but not for the reason you're suggesting. And it's that funny thing about 2. And so I'll change this example next time. All right, let's talk about these. When we look at this, use your exponent laws for this one. 4 times 1 half multiplied by 4 raised to the power 1 half multiplied by 4 raised to the power 1 half. What would we do if we were using our exponent laws? Do the exponent first? Yeah, each would be 2.
Which one are you doing?
4 to the 1 half. So here's the exponent law that applies in this case. Okay, is it? I'll write down different exponent laws. It could be this one: x to the a over x to the b equals x to the a minus b. Is that the exponent law that looks like this situation? You can say no because it doesn't look like this situation. Doesn't look like this situation. Okay, I'll keep going. All right. It's not this situation. X to the a raised to the power b. That's x to the a multiplied by b. It's not that. It's this one. X to the a multiplied by x to the b. What do we do in this case? Kendall. Yeah, we add a plus b here. If we have the same base, we add the exponents together. So this is x to the a plus b. Okay, that's going to be our new exponent that's going to go up there. So let's apply that power law, not these other power laws that I was putting in as red herrings, but it's nice to review. Let's apply that power law. I'll just write the power law nicely and neatly underneath here so that we can see how it applies. X to the a multiplied by x to the b should equal x to the a plus b. So when we do that, what do we have on this side of the equation here? Just 4, yeah. 4 raised to the power, I'm going to write it out for everyone's amusement, 1 half plus 1 half. Okay, if you eat half of a pizza and a little later you're like, I'm still hungry, I'm going to eat the other half. How much of a whole pizza did you eat? It's not a trick question. This video will be called Mr. Jennings Slowly Dies Inside. You ate all of the pizza. Thank you very much. Okay. So this will be, okay, our x to the a plus b is ready. It's 4 to the 1 half plus 1 half. It's just 4 to the 1. What's something to the power 1? I'll give you a hint. I'm 42 to the 1 years old. It's just 4 here. Yeah, I'm not 4. My son is. But in this case, this is 4. Okay, so if we knew, okay, 4 to the 1 half multiplied by 4 to the 1 half is 4, what would you expect 4 to the 1 half on its own to be? 2, yes. And it is not 2 because 4 times 1 half is 2. It's not that 2 for that reason. We'll talk about that in a second. This is 2 times 2. 2 times 2 equals 4. Now let's talk about this one. If you eat a third of a pizza, at 3 o'clock. At 6 o'clock, you're like, I'll have another little bit. And then at 9 o'clock, you're like, no one else is eating this pizza. I'm going to eat one more third. How much of the pizza did you eat? All of it. So this is also 27 to the 1/3 plus 1/3 plus 1/3. This is 27 to the 1 as well. If I told you that x times x times x equals 27, then what would x be?
Q.
Why is it 3, Noah?
That's 3 times 3 is 9, and then times 7 is 27.
Yeah, x must be 3. Okay, so in this case, we can see that 27 to the third has to be equal to 3. This is 3 multiplied by 3 multiplied by 3 will give me 27 to the 1. So today's task is for us to figure out why is 4 to the 1/2 equal to 2 when 27 to the 1/3 is equal to 3. Like, what the heck is up with these fraction exponents is what we're trying to learn today. Any ideas? No? Let's go ahead. Let's take a look at the next few bits here, okay? Oh, wait, so we should write down some things here, some sort of concluding statements. Therefore, 4 to the 1/2 is equal to 2. That's kind of what we were looking to understand. And 27 to the 1/3 is equal to 3. That's something that we were also looking to understand. So I'd get that into my notes. And if you're still like, well, why? I'm not sure. Put a question mark, and all will be revealed if you stay tuned. Okay, so what if I told you that I had a square and its area was 36? How would you find how long one of the sides is? Sorry?
If it's a square, wouldn't it just be, all the same length?
Yeah, so they're all the same length. Let's draw a picture. It's good to draw pictures in these cases. Here's a little picture of a square, and I'm telling you its area is 36. So I want to know, well, then what's its side length? How do you know that you're the mathematician? How did you do that? 6 times 6 is 36. And I'll never forget, because in grade 7, I was sitting there in math class. I was really tired, and it was like, Grant, read the problem in the textbook. And I said, 6 times 6 is 36. And people looked at me like, oh my gosh, because I thought I was saying sex times sex is 36. And I was like, what? And they were all like, did you just say, because I didn't look like I was joking. And then they were all like, did you just say sex times sex is 36? And I was like, no, but I wish I had. That was who I was when I was young. So, yes, we would be solving this problem. X squared equals 36, find x. That's what we're solving. Up until this point, we probably used this tool to solve that, right? The square root of x squared is equal to the square root of 36, right? Yeah? You used to seeing that?
No.
Never.
No.
No? Really?
No.
Like, oh, okay. So if I had, okay, so we're going to do a couple more examples of this. You might want a blank piece of paper. If I have this triangle, okay, and I say this side length is 3 and this side length is 4, and they're joined by a right angle, find me Z there. How do you do that? No, we don't need SOHCAHTOA here. We don't quite need trig. The ancient Greeks were working on these problems before they had trigonometry and side rules and stuff. They may have well had trigonometric principles, but they didn't have our modern trigonometry and our modern calculators. They did have trigonometric principles, but. So what do we do here? 3, 4, and z. Well, we have these kinds of equations. A squared plus b squared equals c squared. To solve this kind of equation, you have 3 squared plus 4 squared equals some number squared. 3 squared you find to be 9. 4 squared you find to be 16. And 9 plus 16 is 25. 25 equals c squared. And then your grade 8 teacher, when you did Pythagorean theorem, would have said we can take the square root of both sides of an equation. That was the part that was missing? Or it was just like, we're going to look at our squares and we find 25 up here? Is that what they did? So I said, we're going to find 25 up there and notice that it's 5 times 5. Is that how they did it? No wonder so many of my students struggle with this. Okay, cool. All right, good. I'm learning too. This is Mr. Jennings slowly becomes alive inside again because when he learns something new, growth mindset here. So yeah, we can take the square root of both sides in this case. Now you might say, but I can just look at it and know 25. That's 5 squared. I know that c must be 5. Okay, Mr. or Mrs. or Smarty Pants here. In that case, well, then solve this one, where this is 60, and this is, oh, this one's actually going to be easy. So it was like, I'll give you a different one. This is 25 here, and this is 60, and this is 60. Sorry, this is 65, and this is 60. All right. Now, we can use the same formula, and it's going to work, but it's going to give us something that we're not going to recognize. Oh, wait. I gave away the answer here. Okay, let's see. And this is x. Isn't this great when I'm ad-libbing? Isn't it just like a wild ride? Yeah, this is fantastic. Okay, 25 squared plus 60 squared equals some number squared. Probably you don't have your squares memorized up to 65 squared. So you won't recognize it when I show it to you. In fact, I don't remember what 65 squared happens to be either. So it's going to be 625, that's 25 squared, plus 660 squared, that's 3,600. And that's going to equal some number squared. Well, this is what you would do on your calculator. You would end up with 4,225. 4225 equals x squared. You would say there ain't no way I can do that in my head. I don't think anyone here can tell me what number squares to 4,225 unless I hadn't just spoiled the fun and spoiled the answer. So this is how you do it on your calculator because we got these calculators that are useful tools. You take the square root of both sides. 4225 equals the square root of x squared. Now the square root of x squared is a silly thing to say. I'm the square root of 42 squared years old. If I square something and then take the square root, that sends it back to itself. It's like multiplying by 1. It doesn't change it. Okay? So saying the square root of x squared is saying find me the thing that when multiplied by itself gives me x squared. Well, that would be x times x is x squared. So that will effectively give me just x on this side. And then this is how you punch it on your calculator, folks. 4225, and then I take the square root of that. Oh, it's 65. Wow. So I have some Pythagorean triples memorized. So sue me. So there, 65. Okay, that's how you do it. You use the square root of both sides. It's just like subtracting from both sides of an equation. It can help you simplify and find your variable. Dividing both sides of an equation by the same number, multiplying both sides of an equation by the same number. Now you can square root both sides of an equation. By now you ought to already have been doing that to solve these types of equations. So in this case, Gabby went old school and says, oh, I just know that 6 times 6 is 36, and I just know it because I'm good at my times tables, not because I have some silly story about when I was 7 and tired. Grade 7 and tired. So in this case, we take the square root of both sides. Or you can look at it like this. Oh, let me just get rid of all this junk. Okay, if it's in your notes, then that's very good. Is you could say, well, 36 is equal to something to the 1/2 multiplied by something to the 1/2. In fact, it would be 36 to the 1/2 on both sides. Because 36 to the 1/2 multiplied by 36 to the 1/2, well, we would add those powers together, it would give us 1. So we can also evaluate 36 to the 1/2, which is the exact same thing as saying, find the square root of 36. The square root here, and we have an index number there that's not there on most calculators, but it is there. It's like it's part of the operation, but we don't usually show it. The same way we don't show raising something to the power 1 or dividing something by 1. It's just something that we don't need to show. But in this case, if I had 27 sugar cubes arranged into a larger cube, and I wanted you to draw a picture of that, how many sugar cubes would be in a single face? How many sugar cubes would be lined up along a side? Well, I know a cube is volume. It's length times width times height. And if I have 27 such cubes, then I must have the length times the width times the height equaling 27. But because it's a cube, and I can draw a picture of cubes, not very well, but I can. Math teachers are not known for their artistic skills, generally speaking. There is a picture of a cube. And in a cube, this is the same length as that, is the same length as that. The length, the width, and the height are all the same. So I can call this just like the length to the power 3. Or I could also write length times length times length equals 27. Some number multiplied by itself 3 times to give me 27. So can people see what value length is here? One way of doing this, and this is the way most students are comfortable with by this point, is I have length cubed is equal to 27. So instead of taking the square root, we would take the cube root of both sides. The cube root of L squared is like saying, L cubed is like saying, find me the thing that when multiplied by itself 3 times gives me L cubed. Well, that would be L. In this case, we know L cubed is 27. So I can punch that on my calculator this way. 27, and I go second function, and notice I have a cube root there. Can you see that? It's a little 3 inside there, inside the cube root. I don't know if I can I zoom here for you? No, I can't. I take the cube root of that, and it tells me it's 3. The cube root of 27 is 3. 3 times 3 times 3 is, as Noah identified before, 27. Another thing that we can look at this, a new way, is by looking at this as, well, I could write 27 in a funny way, this way. I could say 27 to the 1 is equal to 27 to the 1/3 multiplied by 27 to the 1/3 multiplied by 27 to the 1/3. When we have exponents that are fractions, it's like taking the nth root of that number. Meaning, how many times do I need to multiply this number by itself to give me that number? This many times. Okay. Here is a way of thinking about all of those different numbers in a type of formula here. Okay. If we have an x raised to a fraction, the fraction is going to have two parts, a numerator and a denominator. In these cases, the denominator is the one that goes into that little function there. That means the nth root of something. And then this one still just stays an exponent and acts like other exponents that we've seen before. As we take a look at some examples, I hope that this type of thinking becomes a little more clear and you'll see how to manipulate these types of thinking. Another thing that you can be looking at is in your handouts, you have this chart of numbers that you filled out in the first lecture where you raise 2, 3, and 5 to different powers. As you're working on these problems, take a look and see if the numbers that I'm giving you in these problems show up in any of those places. And that will help you understand these types of problems. So let's go forward here. And then I gave you this little diagram there to have in your notes to see how you go between this form and this form over here. Let's try it. If we have 27 and we're going to raise that to the 2/3, let's find out what that is. Okay? And we want to write this in what's called a radical form. These numbers, if you have something in there like 5, that type of number is called a radical. If I have a different index number, it's still a radical. Even if I want the 31st root or something, that's still a radical. Okay, so if I want to write this in radical form, I remember that x to the a over b is equal to, well, the b root of x raised to the power a. And so I can use this little recipe to rewrite this in a new way. And let's try that. So let's go in here. 27 raised to the power 2/3. I can transform that. I know this number here is the thing that goes inside that little machine, that number machine. 27 is the main number. The base is still there. And then this number can come outside and be the exponent that I raise things to the 2. Okay. Now, the third root of 27. We can also write this, and I prefer to do it this way. 27, but some students that are already comfortable with this notation will like that better. Both are fine. I write it as 27 to the 1/3 to the 2. And then I notice that if I use my power laws, x to the a raised to the power b equals, I multiply those exponents, x to the a multiplied by b. So here, 1/3 times 2 would give me 2/3 back. So I know that these two things are equal to one another. And now I can evaluate either the third root of 27, what number multiplied by itself 3 times gives me 27? 3. So let's rewrite that. Notice it's the same problem there as it is there. 27 to the 1/3 means find me the thing when multiplied by itself 3 times gives me 27. Whether I write it one way or another, it's the same. So both of these problems come down to 27. Oh, sorry, not 27. 3. 27 to the 1/3 is 3 raised to the power 2. 3 squared? 9. Final answer. 27 to the 2/3 equals 9. Now, let's take a quick look, and if you can sketch a graph on your page, that would be great. If not, create a new page. Find a spot where you can make a graph in your work somewhere. Let's take a quick look at Desmos. We're going to zoom in here, not on my face, which is not very useful in this situation, unless you're only here to see me die inside. We're going to look at values up to about 30. Okay, and we're only going to look at x values up to about 1 here. All right, so there is, and here we write 27 raised to the power x. Okay? Notice that when 27 is raised to the power 0, unsurprisingly, it's equal to 1. Anything raised to the power 0 is 1. So 27 to the power 0 should also be 1. That doesn't surprise us. But when we raise 27 to the power 1, it's itself. There's the point 127. Also not surprising. Now let's take a look at things like x equals 1 over 3 and x equals 2 over 3. And let's find out what it equals at those points. X to the 1/3, 23 to the 1/3 gives us 3. 27 to the 2/3 gives us 9. And notice that as we look at these fractional points, these fractional exponents, these are the points that complete a smooth curve, a smooth growth curve between 0 and 1 for values of x. And Desmos is suggesting we should also be able to take 27 to the whatever we want. Any kind of number, and we'll get weird decimals in between, but because 27 is itself a cube, that's 3 cubed, we get nice values at the thirds. All right. Let's take a look at 64 to the x. And we're going to now look at values of y up until about 70. Here at 64 to the x, does it give us clean things at the 2/3 and at the 1/3? Yes, it does. 64 to the 1/3 is giving us 4, and 64 to the 2/3 is giving us 16. What's 4 raised to the power 3?
64.
64. Notice that 64 to the 1/3 is 4. 4 to the 3 is 64. And that's a fact family. That's like an exponent fact family, in the same way that 2 times 3 is 6. So 6 divided by 2 is 3, and 6 divided by 3 is 2. Fact families. Multiplication and division makes fact families. And these exponents to fractional exponents also create these fact families. And if you're looking for these fact families through the problems we look at today, you'll also find that they're there as well. We'll also have another nice one at x is equal to 0.5. If x is 1/2, this will give us 8, because 8 squared is 64. And notice again the smooth curve that joins all of these points. Let's keep going. Okay. Radical to rational form. So now we also want to be able to rewrite stuff like this as fractional exponents. So let's do exactly that. We're going to use our little formula here, our little recipe, which is if we have b, the root of x raised to the power a, that's the same thing as x to the a over b. So in this case, the fourth root of 16 to the 3 is going to equal, well, 16 is still the base, 3 is the numerator, and 4 is the denominator. And now, before we go forward, we would guess that our answer here would be less than 16, but bigger than 1. What would you guess this answer is here? 16 to the 3/4. We need to break it down and take a look at what it is. Yeah, so that would be if I use multiplication, but it's not quite that. Yeah. 2 is part of the answer. So let's take a look as we break this down. I like to break it down this way. 16 to the 1/4, meaning find me the number that multiplied by itself 4 times gives me 16, and then I'm going to raise that number to the power 3. Notice that 1/4 times 3 would give me back that exponent, so I know that these two lines are equal, because I use my power laws in reverse to break that apart. What number multiplied by itself 4 times gives me 16? 2, good. So 16 to the 1/4 is equal to 2. And then I'm going to raise 2 to the power 3. What will that be? It will be 8. Very good. So this is 8. Shall we take a look at this in Desmos? Of course we should take a look at this in Desmos. Let's take a look at 16 to the x. So that's our base function here. I'm going to just zoom in a little bit so it's easier to read from the back of the room. 16 to the x. And I'm interested in when x equals 3/4. So 3/4. Oh, 3/4. There we go. And so here is, and we're just going to change our zoom level so that we see the y values a little more clearly. There we go. So here is 16 to the 1 is 16. And if I follow the smooth growth curve back, 3/4 the way to 0, I get to 8. And there it is. That's 16 to the that. If I look at the 0.5, that'll be 4. That's 16 to the 1/2. 16 to the 1/2 is like saying, find me the number multiplied by itself gives me 16. That's 4. And then 16 to the 1/4, that's back here. We found that already. No, it's over here. There it is. 16 to the 1/4 is 2. There. Find the right pixel. There it is. 16 to the 1/4 means find me the number multiplied by itself 4 times gives me 16. And then we cube it. So that's 8. Keep going. Solve each. 36 to the 3/2. How do we get started with this problem? Did I start the video again? Yes, I did. Good. How do we solve this problem? 36 to the 3/2. I like to start these solutions with an equals sign, Mr. Jennings. I like to do that because it shows my reader that this thing over here is going to be equal to the next thing I write. Oh, good idea. Okay, what do I do next? Yeah? Yeah, I do 36 to the 1/2, and I bring that 3 outside the bracket out there. So this is 36 to the 1/2. And then I interpret 36 to the 1 over 2 as kind of a backwards exponent. Like I want to find the number that when multiplied by itself twice gives me 36. That number is, yes, good. So we can then simplify that. 36 to the 1/2 is 6. And then I raise 6 to the power 3. Well, what's 6 to the power 3? Use your calculator if you don't know. Or write it out. It would be 36 times 6. Give you a hint. It's 36 times 6 because 36 is 6 times 6. Then you just have to multiply by another 6. So it'd be 36 times 6. 216. 216 is correct. 30 times 6 is 180. 6 times 6, we already knew, is 36. And then 180 plus 36 is 216. So this is equal to 216. How about 27 to the 4/3? Oh, I agree. The first thing I do here is an equal sign. Very good. Pat yourself on the back if you already have an equal sign. And then just bust it up like you're busting it up. How do you bust this one up? We have here the denominator. Do that part first. 27 to the 1/3 is not 9. I'm not multiplying by that exponent. I want to find the number that when cubed gives me 27. And then I raise that to the power 4. This number comes out here. This number goes there as the bottom of a fraction. So what is this? 27 to the 1/3. What's that? Yeah, 3 to the 4. And what's 3 to the 4? No, that's 3 times 4. But remember, 3 to the 4 means 3 times 3 times 3 times 3, not 3 times 12. Did you say? It starts with an 8. 81. And here's how you could do that a little easier. 3 to the 4 is equal to 3 squared times 3 squared. What's 3 squared? 9. What's 9 times 9? 81. It's one of my son's favorite math facts. He loves that 9 times 9 is 81. We used to live at 81, so maybe that's why he loves that fact. And he's very interested in square numbers. So this is equal to 81. Good. So 27 to the 4/3 is equal to 81. I don't expect you to have that memorized, but I do want you to have this skill of break up the exponent into 2 pieces, evaluate this piece, and then raise it to that piece. That's the skill that you want to develop today. Okay, so now what if we have negatives? Oh my goodness, negative exponents. It got harder. That's crazy. Craziness. What if I told you that it only adds 1 step and that the step is easy? And despite it being easy, my university level students will still tell me crazy things, and you all will still tell me crazy things until you stop. And it makes sense for you. So, when you have a negative exponent, think of this as like a 3-step exponent now. I have this step, and that step. So it's an elephant that I can eat in 3 bites. I don't want to try and eat it all in 1 bite. I might choke. You still need a very big mouth though, don't you, Willen? So, first step is to deal with the negative. Get that out of the way. If I have x to the negative 1, that's equal to 1 over x. If I had x to the negative 2, that equals 1 over x to the 2. You see, the job of this exponent is just to kick that thing downstairs. On the other hand, if I had 1 over x to the negative 1, that would be equal to x. If it's downstairs, it kicks it upstairs. If it's upstairs, it kicks it downstairs. And that's all the negative exponent does. Is if you're multiplying by that thing, it says, no, please divide by it. If you're dividing by that thing, it says, no, please multiply by it. It just changes the floor in which you find that number on. And that's it. That's all it does. It does not change the sign of the number, doesn't change it from positive to negative. It doesn't do those things to the number. It just takes your base and puts it on the bottom if it was on the top. If it was on the bottom, it takes it from the bottom and brings it to the top. If you had something like this, a over b to the negative 1, well, that would be equal to b over a. Takes what was on the upstairs and puts it downstairs, takes what was downstairs and puts it upstairs. It's just a big furniture rearranger. That's all the negative exponent does. So let's use that idea here. We're going to start with an equal sign to tell our reader what we write over here is going to be equal to what we write over there. And we're going to write it this way, 1 over 64 to the 1/2. All we did was deal with that negative there. We keep the exponent, and we'll evaluate it in the next line. 64 to the 1/2, but it's on the bottom of this fraction. What's 64 to the 1/2? Good. I was wondering if you were looking at the clock or the multiplication table. I was hoping the latter. So I'm glad you came back with the answer. Yes, 8 times 8 is 64. So this is a set of instructions here that says, go find me the number that when multiplied by itself twice gives me 64. That number's 8. So great. So 64 to the negative 1/2 is equal to 1 over 8. It's just an eighth. And we're done. We have finished. How about 1/8 to the negative 1/3? All right. Let's first deal with the negative part of the exponent, and then we'll deal with this fraction bit later. So we'll use an equals sign, and I've got a fraction there already. Well, I kick what is downstairs upstairs, and I kick what's upstairs downstairs. And I'm not going to write 8 over 1. Can't make me do it. Okay, you just got to know that numbers are all over 1. 36 over 1 is 36. 8 over 1 is 8. So 8 to the 1/3. There. That's what this negative exponent is telling me to do. It's telling me flip this. Flip this base. All your base are flipped by negative exponent. Okay. Now what's 8 to the 1/3? Yeah. So the answer here is 2. The answer here is not negative 2. Please stop thinking that the negative exponent means you have to change the sign of the number. It's not that. It's just flip it. Okay. Equals 2. Okay. And then if we look at some of these curves here we have 16 to the x. If I look at the situation where x is negative 1/2, I'm going to get 1/4 here. Notice that negative 1/2 gives me 1/4. Why is that? Well, 16 to the negative 1/2 would be 1 over 16 to the half. The number that multiplies to give you 16 is 4. 4 times 4 is 16. So the answer is 1 over 4. That's why 16 to the 1/2 does that. Notice that these exponent rules create smooth curves. They don't bounce all over the place. I get my university level students saying, my graph, all the points are good except these points are all over the place. Oh yeah, it's because you're not doing it right. It's not the graph's fault. It's the teacher's fault for not showing you this the right way the first time, I guess. So here I am trying to show you the right way. Okay, I think that's all the examples that we had to go over together. Yeah, so do I have anything else on the handout? Solve for x? Here. Yeah, some solve for x stuff. So let's say you have these problems and you want to solve for x. Let me show you how you can use this idea of fractional exponents to solve all these types of problems now. As I was saying, the old way to solve for this was to take the fourth root of both sides. But you're telling me that you didn't do that before anyway. So I'll give you a new way. And the new way is to raise both sides of the equation to the 1/4. How did I know to do that? Well, I take the exponent that's in there and I write it out. 4 is 4 over 1. And I know that if I flipped that and multiplied, I'd get 1. So 4 over 1 times 1 over 4 gives me 1. And that's true for any fraction. 2/3 times 3/2, see it in your mind, 2 over 3 multiplied by 3 over 2 equals 1. If you ever multiply a fraction by its flip, you get 1. And I can show you that with exponent laws too. I'll do that later. Okay, so then x to the 4 to the 1/2 is I multiply the powers. So that's x to the 4 over 4. That's 1. And that's equal to 16 to the 1/4. Well, we've already done that before. It's 2. Okay, 2 times 2 times 2 times 2 is 16. I have to multiply that number by itself 4 times to get 16. So that's 2. And so then that's x equals 2. X to the 1 equals 2. Done. In this case here, I have x to the 3 over 2, and I'm going to raise both sides to the, you guessed it, 2/3. And now 27 to the 2/3 is a problem we've already solved. It's 27 to the 1/3 squared. Just break up that fraction into two pieces. X to the 3/2 times 2/3, that's just x. That's x to the 1. And then 27 to the 1/3 is 3. So x is equal to 3 squared. X is equal to 9. Now, go back and test it in your initial equation. 9 to the 3/2. Do it in your head. 9 to the 3 over 2. First, I do 9 to the 1/2. That means find me the number multiplied by itself gives me 9. That number is 3. 3 times 3 is 9. And then I remember, well, I was doing not 9 to the 1/2, but 9 to the 3/2. So I need to take the answer 3 and multiply it by itself 3 times. And I find that, yes, indeed, that is 27. So 9 satisfies that equation. And notice that when I do that little bit of work in my head, I will catch a mistake if I've made one on the test. But when I'm doing that, rather than just like flip to the back of the book and check the answer, if I check the answer myself, and maybe you're laughing because you don't have this habit of flip to the back of the book and check your answer. It's still a good habit. But if you check the answer yourself, you're building that understanding a second time by going through the problem backwards. So that's just a part of your practice flow that I'd encourage you to have. Okay, so that is our topic for today. This is a cool trick that you can use, raising things to fractional exponents on both sides to clear away an exponent from a variable if you want to solve for that variable. It's not really a skill that I'm going to test, but you do definitely want to be able to evaluate rational exponents, fractional exponents in this course. Okay, so wrapping it up here, and then what do we do to practice?